Hypothalamus Artificial Intelligence, HAI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the conference Oil Production. Linking Optimization and Simulation Models. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. Topic: Oil and gas reservoir, numerical reservoir simulation. A petroleum reservoir of oil and gas is a subsurface accumulation of hydrocarbons, contained in porous, or fractured rock formations. Such reservoirs form when kerogen, ancient plant matter, is created in surrounding rock, by the presence of high heat and pressure in the Earth's crust. Petroleum reservoirs are broadly classified as conventional and unconventional reservoirs. In conventional reservoirs, the naturally occurring hydrocarbons, such as crude oil or natural gas, are trapped by overlying rock formations with lower permeability, while in unconventional reservoirs, the rocks have high porosity and low permeability, which keeps the hydrocarbons trapped in place, therefore not requiring a cap rock. During the production of oil and gas, water is obtained as an additional material. Reservoirs are found using hydrocarbon exploration methods. Numerical reservoir simulation is an area of reservoir engineering, in which mathematical models are used to predict the flow of fluids, typically, oil, water, and gas, through porous media. Traditional finite difference simulators dominate both theoretical and practical work in reservoir simulation. Conventional physical simulation is underpinned by three physical concepts: conservation of mass, isothermal fluid phase behavior, and the Darcy approximation of fluid flow through porous media. But it should be noted that finite element models are a higher precision alternative, and as expected, higher computational cost. Thermal simulators, most used for heavy crude oil applications, add conservation of energy to this list, allowing temperatures to change within the reservoir. The finite difference model, FDM, consists of a model grid that is partitioned into rectangular, 2D, or cuboid, 3D, pieces, called cells. Each cell can be further discretized, which means, parted into smaller cells, to obtain higher resolution of the model, to get a better accuracy of the calculation, if sufficient data are available to warrant the higher resolution. The refinement of the grid occurs vertically and/or horizontally of the area of interest. The model calculates the governing differential equation, by approximating the derivatives of the finite difference equation for each cell. In other words, consider a point in space where an infinite equation is replaced by sections of the equation, the finite difference equation. This solving approach works well with regular rectangular, or square-shaped elements, and requires less computational effort. The finite element model, FEM, consists of a mesh with irregular triangular, 2D, or quadrilateral, 3D, elements. An element in a mesh of a finite element model can be compared to a cell in a grid of a finite difference model. Different than a FDM model, in a FEM model calculations are carried out on the nodes, which are the vertices of each element. Due to the flexibility of a mesh, the model can represent the exact geometry of an irregular model shape. Furthermore, the discretization can be refined locally, around the area of interest. This approach can achieve higher accuracy, in exchange for higher computational effort. FEM models are preferred where model geometry is of importance, such as the modeling of the aerodynamics of a plane, F1 racing car, or a space shuttle. For oil reservoir, surface water and groundwater modeling, both FDM and FEM are suitable. The accuracy of model results does not only depend on the solution method, but more on the ability to translate the problem into a conceptualized model and model development, proper discretization, accuracy of the input parameter, and the calibration quality. In the case of the simulation of surface flow in a river, in which there is a well, the figure shows how a real-world situation is conceptualized in the mathematical model, and how the river and well are represented in a FDM model using a finite difference grid, with greater resolution near the well. Due to the shape of the cell, rectangular or square, the FDM model domain often expands beyond the model area. However, these areas outside the principal area of interest in the model must be assigned as inactive cells to eliminate unnecessary cells. The same figure depicts a mesh refinement for the same, River and well to make a simulation using a FEM model. FEM models formulate the partial differential equation for each node, and the results are then put together into one solution that is reasonable for the entire domain. The oilfield simulation model must consider the geological model, or the reservoir description, the expected properties of fluid, the impact of the operation of the wells, the facilities available, and the historic production data, oil, gas and water. As an output, the model must produce the movements of fluids inside the reservoir, and the pressures in the place of collection of the wells. Like any simulation model, the operation of wells must be defined exogenously, either by an expert engineer, or by an artificial intelligence. Simulation models do not have the ability to optimize decisions. They must be modified or linked to an optimization model. The source used to present the characteristics of the numerical reservoir simulation was extracted from the reports made by Dr. Zhangxing, John, Chen, of the University of Calgary, published on his website. The presentation made at this conference is a short summary, and only informative. Its purpose is to introduce the simulations models, in order to explain their link with the optimization models. For people with greater interest, it is suggested to watch the images carefully, and, if they consider it convenient, to contact Dr. Chen. Reservoir simulation is a developing application technique for reservoir development and management. It can be used to forecast the production behavior of oil and gas fields, optimize reservoir development schemes, and evaluate the distribution of remaining oil through history matching, for example. It is an important tool to help reservoir engineers optimize the design of well development schemes, improve the efficiency of reservoir development, and enhance oil and gas recovery. The following aspects must be considered: continuous formulations, mathematical modeling, scanners and grid generators, numerical discretization methods, linear system solvers, solution schemes, visualization and post-processing, applications, and experiences. The governing equations that describe multi-phase flow in reservoirs are nonlinear and coupled. They can be rewritten in different differential formulations, so that the coupling and nonlinearity of these equations are weakened. The software developed for the numerical simulation of reservoirs includes scanners that facilitate the generation of 3D grids. Many discretization methods have been applied to the numerical solution of the flow and transport equations in reservoirs. These methods range from finite difference methods, finite element methods, discontinuous finite element methods, control volume finite element methods, mixed finite element methods, to control volume function approximation methods. Their limitation, efficiency, accuracy, flexibility, and applicability to reservoir simulation have been described and compared. In particular, the software presented by Dr. Chen has been developed and applied to control volume function approximation method. Fast and accurate solution of linear systems of algebraic equations that arise from the discretization of the governing equations for multiphase flows has been increasingly important. In a numerical reservoir simulator, about 80% of time is spent on the solution of these systems. There are many solvers to this type of mathematical models. Since the fluid flow and transport models in reservoirs involve large, coupled systems of nonlinear, time-dependent partial differential equations, an important problem in numerical reservoir simulation is to develop stable, efficient, robust, accurate, and self-adaptive solution schemes. Dr. Chen has developed an improved IMP scheme for solving two-phase flow in three-dimensional reservoirs. Dr. Chen have developed parallel codes for thermal simulation of multi-component, multi-phase fluid flow in petroleum reservoirs. These codes utilize the Message Passing Interface (MPI) library, overlapping domain decomposition, and dynamic memory allocation techniques. Numerical results for these simulation models indicate that these parallel codes can significantly improve capacity and efficiency for large-scale thermal simulation. A successful application of visualization technology to reservoir simulations can help reservoir engineers study more accurately physical data, such as the porosity, permeability, depth, and thickness of reservoirs, construct more accurate geological and flow models, and perform more realistic simulations. It also helps them view and analyze water, oil, and gas distribution and history matching. As simulation technology gets more advanced, there are new requirements from reservoir engineering. The features of Dr. Chen Reservoir Simulation Model are black oil flow, extended black oil flow, compositional flow, dual porosity and single dual permeability, and thermal flow. The numerical reservoir simulators can apply to primary depletion, water flooding, dry gas injection and gas cycling, undersaturated and saturated reservoirs, investigation of displacement mechanisms in both fractures and matrix blocks, treatment of volatile oil, gas condensate reservoirs, coning studies, WAG processes, steam injection, interpretation of pressure drawdown and buildup tests for wells, modeling of slanted and multilateral wells, and aquifers. Topic: Topology optimization of continuous structures. As previously stated, when object geometry is very important, the FEM models are preferred. For example, in modeling of the aerodynamics of an airplane, a non-optimal curvature may involve millions of dollars in fuel consumption over its lifetime. All the above implies that the optimization process is complex, due to the nonlinearities in the model of finite elements, or finite differences, that represents the object to be optimized, and the ignorance of the derivatives of the objective function, as a function of the optimization variables, which are typical of the topology of the object to be optimized. For example, in the case of the aircraft, it may not be clear how the fuel consumption derivative behaves, as function of the variables that define the curvature of the aircraft's wing. It is possible to know its direction of movement, positive or negative, but it is very difficult to know its magnitude. The indicated process is linking an optimization model with the simulation model. The fundamental hypothesis of the methodology to be proposed assumes that the derivatives of the objective function, due to all impacts on changes in design variables, are continuous, and therefore a gradient-based optimization process could be carried out. Let K be the iteration of a gradient-based nonlinear optimization algorithm. A mathematical method can be implemented to estimate the gradient, and possibly the Hessian, of the objective function as a function of the design variables, which we will call xk. Automatic differentiation, AD, also known as algorithmic differentiation, is a method for evaluating derivatives of a function expressed as a computer program, in this case the simulation model. AD is based on the fact that any computer program that implements a vector function z equals phi of x can be decomposed into a sequence of elementary assignments, each being trivially differentiable using a LUT lookup table. These basic partial derivatives, evaluated using different values for the argument xk, are combined according to the rule of the derivative calculus chain, to generate information for phi of xk, such as gradients, tangents, the Jacobian matrix, the Hessian matrix, etc. This process obtains exact derivatives, according to numerical precision. Because symbolic transformation occurs only at the most basic level, AD avoids the computational problems inherent in complex symbolic calculus. Based on the above assumptions, an algorithm can be formulated for optimization of a nonlinear objective function. Two extreme alternatives may be considered, quite well known. Maximum ascent algorithm, moving in the direction of the gradient in xk, for the case of maximization, and Newton's method, which calculates the optimal point in the vicinity of xk, based on a Taylor approximation of order 2, which combines the Hessian with the gradient. Between these two methods, there is a wide variety of algorithms, which improve the behavior of the maximum ascent, without the need to invert the Hessian matrix in each iteration. In addition, it is necessary to include constraints in the optimization process. The connectivity for optimization oil reservoirs is presented in the image. Topic: Oil and gas reservoir modeling operations using the linear response theory. In this case, the Oil Pro model answers, among others, the following questions related to oil management, at the level of the underground reservoir that contains it. Where should injection/extraction wells be located? At what rate should oil be extracted in each well? To which rate should water be injected into each well? And to which rate should gas be injected into each well? Oil Pro provides as a solution that maximizes, or minimizes an objective function, which satisfies all the physical constraints of the oil field, and the operational constraints set by the user. A typical goal may be to maximize the total pumping rate of all oil wells, while constraints may include upper and lower limits on load heads, gradients, and pumping rates. As in the previous case, the chaining of two models is required, optimization and simulation. The approach of this link is different. The theory used is the linear response theory and reservoir systems. The models supported by the linear response theory for the oil reservoir system are based on the principle of superposition, which respects two fundamental hypotheses. Multiplication in the injection, O extraction rate, proportionally impacts the drawdown at each point in the reservoir, and the result, drawdown, induced by the simultaneous action of more than one well, is equal to the sum of the impacts generated by each well individually. Linear response theory is not always applicable, but in numerous cases it is a reasonable approximation. The alternative of a nonlinear response theory can be considered, but it significantly complicates the optimization process. The linear response theory is synthesized by means of the reservoir response matrix, which relates QA, the rate of injection or extraction, of gas and/or water, and QB, the rate of oil extraction, with the change in pressure SI, at the selected control points. The example considers I is equal to 1, 2 or 3. The response matrix must be estimated, by conducting experiments with the simulation model, and is the link between the two models. The image presents linear response theory for an example of groundwater optimization. If the number of control points is very large, the evaluation of the matrix should be analyzed. If the number of control points is manageable, the full matrix can be included directly in the optimization model. This situation can occur in operation optimization problems, where the number of wells is known before the problem is resolved. It may have to be included within the cycle of the algorithm, based on techniques of partitioning and decomposition of optimization problems. This situation can occur in design problems, in which each point of the grid may be part of the optimal solution, which can generate problems of mixed optimization of high dimensionality. The simulation optimization approach is more efficient than simulating a small number of pumping scenarios, through trial and error, in order to manually determine the best solution. Additionally, it yields a much cheaper result than the simulation-only approach. This type of model may be applied to subsurface oil management problems, formulated in terms of oil, water, and gas flow. Oil exploitation network design. Equivalent to a supply chain design problem, in which the objective is to maximize the long-term oil recovery in the reservoir. Planning of sales and aggregate operations of oil fields, S&OP. Oriented to manage the operation of the reservoir in the medium term. Programming of the operation of the oil reservoir. Scheduling operations in the short term. The diagram shows the integrated oil reservoir resources decision support system, that considers models for all levels of the hierarchical chain of decisions, strategy, tactics and operation. The types of restrictions offered by Oil Pro are divided into four main categories. Hydrogeological constraints based on linear responses, which establish limits on head difference, drawdowns, gradients, velocity, and relative gradient or flow direction. Balance constraints, based directly on extraction rates at each well. Integer constraints, to select X active wells between the potential locations. Limits on extraction, or injection rates in individual wells, and control of extraction of derived, or complementary materials, such as water and gas. This modeling may become a non-anticipative stochastic optimization model, to describe the uncertain process of oil availability in the reservoir, and other random parameters, like prices, demands, etc. This approach should be included, to manage the integrated problem of long-term strategic planning, of the order of years, and that of medium and short-term tactical planning, of the order of months, weeks. It should also be considered that stochastic optimization models are the basis for incorporating financial risk management into mathematical modeling. Optimization knowledge expert systems. The current computing power makes it possible to design complex optimization processes, in which information is exchanged autonomously between models. One of these concepts is the artificial hippocampus, which corresponds to the vision of expert systems, traditional in artificial intelligence. For cases of high dimensionality, for example, oil fields with many wells, or oil field design processes with many possibilities, the production of the elements of the response matrix can be accelerated, considering the availability of CPU processors, which currently has an oil company. The basic idea is to think about to include the simulation model within the optimization model. This is a viable idea, but it involves high complexity in mathematical formulation and high computation times. The production of the elements of the response matrix may be a standalone process, therefore, they can be generated outside the optimization process, and may be storage in an optimization knowledge database. Then, the elements of the response matrix will be used by the coordinated optimization model, when the optimization process requires this information. If large-scale optimization methodologies are used, it is possible to establish a dialogue between the information system and the optimization model, as the optimization process progresses, decreasing the dimensionality of mathematical problems and speeding up solution times. It should not be forgotten that the cases in the real world are complex and of high dimensionality. For example, it is quite possible that be necessary to coordinate simulation models of multiple reservoirs. Topic: Integration of reservoir modeling with oil field planning and infrastructure optimization. This topic is based in work realized by the Center for Advanced Process Decision-Making, CAPD, of the Carnegie Mellon University. The approach of the modeling is to have a simplified simulation model as part of the optimization model equations. This model will take input parameters from the simulation model. The model is a mixed nonlinear programming problem, MIN-LP. The main constraints are discretized reservoir correlations, nonlinear pressure drop correlations, well placement equations, and component flow rate bounds. The components of the objective function are oil sales income, total liquid production cost, total water injection cost, and drilling cost. These economic values are sum over all the periods of the planning horizon, discounting them based on the beta discount factor. It is assumed that a 3D simulation model of the oil reservoir is available, from which a 2D grid must be obtained, to summarize the behavior of the reservoir at surface level. The irregular-shaped reservoir is fit to the tightest possible rectangle, followed by dividing the rectangles into cells. All adjacent cells are transitively interconnected. The cells of the grid are classified into potential producer wells, injector wells, and boundary cells, in which wells are not considered possible. The reservoir dynamics is expressed based on the following rules. The equations are discretized in two directions, indexed as I and j. The cell number n is given by the I plus j1, multiply by I, where I, capital, is maximum index in the x direction, and the boundary cells are not considered for calculations. The parameters of the model are volume of grid element, in cubic meters, step size in days, and transmissibility in x and y direction. The variables calculated by the model are variable accumulation multipliers, mobility of fluid in x direction, mobility of fluid in y direction, pressure, water saturation, and total flow rate. The F subindex represents oil and water. As a result of the movements of oil and water in the reservoir, two balance equations must be satisfied, which determine the pressures and quantities of oil in each cell. The first equation defines the dynamics of the reservoir over time, relating T to T plus 1. The second equation defines the special dynamics, relating cell ij to all its neighboring cells, for each period t. In this way, a simplified simulation model is included as part of the optimization model equations. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.